Hello and welcome to the lecture on game engines. This will be cross-cutting lecture touching various parts of a game engine architecture while focusing a lot on its foundational levels, because that is making the topic unique in the context of game development. Supporting gameplay, AI, animations, etc. are to be discussed in other lectures focusing on them, but memory, asset streaming, timing or jobs are game engine specific topics. But first, let us ponder, why do you need game engine? Of course, you need to run the game somehow. But why would you like to utilize third-party game engine for that? The answer is not as obvious as it would seem. The problem is that when you choose game engine for a particular feature X, you might later find that your game also needs particular feature Y. Your chosen game engine is not prepared for, or the support of that feature is cranky and you have to work around it a lot. And that's what this lecture is about, to give you impression what all game engines may consist of, some tricks how they do that, some technicalities here and there. In the end, you should be able to compile a list of questions that you could try answering when assessing particular game engine for your game production. So why or for what purpose do you seek game engine? First, you are working single, but you want to make 3D game, for instance, and you're not much into rendering and you want all those nice shadows and post-processing effects, for instance. Or you're a studio that employs a lot of people like 10, 20 or more, and you want them to collaborate on a single game. Common denominator is thus efficiency. You seek to speed up your development. How can Game Engine help with that? To understand and discuss how Game Engine can help, we need to first describe what Game Engine is. We can characterize game engines, as they are quite a few, actually a lot of them, as a set of tools for easing game production. You might see them through prism of their editors, but during development you might actually need console tools as well for automating your pipeline, like for instance automatic compilation and builds that you can distribute to your testers on a daily basis. But it is true that their biggest feature is usually an integrated game development environment paired with some IDE for coding, which might sometimes be even integrated in the engine itself. You probably expect game engine to be also game agnostic, meaning extensible and reusable. Though that might not always be the case, as it depends on what features and of what quality the engine is integrating. Multi-platformity is a must today, of course. Even indies are trying to target as many platforms as they can to reach broader audience. The problem is that many games, once built, resemble some kind of engine, because iterative development and remaking of bits here and there is part of all game development. So each game can be, to a certain degree, modded to create a game of different aesthetics or different storyline. So each game and engine can be put on a hypothetical timeline, where on the left side we have so rigid implementation that it cannot be easily changed, and on the right side we have the holy grail of game engines, something so flexible that it can be effectively used for creating lightweight 2D platform to full-fledged 3D MMOs. Interesting is then comparison between Quake 2 or 3 engine, Unreal Engine 4 and Unity, each quite different. But Quake is for first-person shooters, while Unreal Engine was also built for first-person shooters originally, whereas Unity is more in game-agnostic part. But as development of UE4 continues, it is getting more and more general. Now, having some kind of idea what game engine is, one might ask what is the difference between a game engine, a game framework, or a middleware. Typically, it is in the amount of features they provide you with. Frameworks and middlewares usually do not provide integrated environments, or they have specific one designated for single purpose. Framework is usually integrating a few subsystems, usually enough to create simple games, and they differ from middlewares that they are still featuring execution loop, that is, implementing the game loop design pattern we will be talking about at the end of the lecture. So that was an answer to what is game engine. Now for whom those game engines are built, whose requirements are shaping their development and in which way. Before diving into an engine architecture, there is important remark about the different kinds of people who are working with a game engine. That's because game engine is not here only to support the game, but the work of game makers as well. That is, game engine contains a lot of tools and code that is actually irrelevant to the game itself, but which is extremely important during the game production. The program that runs the game can then be run with just a subset of the whole game engine codebase. How easy it is to work with a codebase, import new content, script, new game mechanics is a very important aspect of every game engine, as the game can never be designed using waterfall schema. Interactivity must be directly experienced, and it is very hard, if not impossible, to fathom. Therefore, the engine must support iterative development and ease the cycle of designing, coding, assembling, and playtesting as much as possible. So you have engineers who need to code efficiently, artists who need to create and integrate content as fast as possible, and game designers that need to efficiently iterate their ideas. Game Engine can be then seen as an integrator of their work. Finally, your target is not to use the game engine but produce a game. So what kind of features a game engine should support or allow for? Unfortunately, that's a multidimensional problem. Each game is different, has different needs, and stresses the quality of different game components. What some games do not need might be a killer feature for others and vice versa. Moreover, engines should allow extensions if developers find it lacking a certain feature. There should be a way for dealing with that. So there is no black and white division what belongs to a game engine and what's not, though there are definitely parts all games need. If we look over the landscape of game genres, we will find out that different genres are requiring different gameplay or game world features. Like FPS RPG, large 3D worlds, responsive camera, weaponry magic, minimal character model, high fidelity animation and small scale multiplayer. Platformers, dynamic environment, puzzle-like elements, third person and complex camera movement. Fighting games, rich set of fighting animations, accurate hit detection, complex user input, single arena only. Racing games requires tricks for distance object rendering, track divided into reusable sectors, and third-person kinda complex camera movement. RTS, hordes of low-res units, terrain, adjustable environment, buildings at least, various UIs, a lot of them actually, and point-and-click interface. And mass multiplayer games require scalable networking subsystem. And this is non-exhaustive list for sure. That's the reason game frameworks still exist, as they can be extended clearly according to the need of the concrete game. For a game engine, changing one block that does not work well for a particular game can be cumbersome to extremely hard. For all those reasons, choosing a game engine is hard. Practically, you have to first decide on what your game is going to be about, what is going to be its killer feature, what elements will need to be of high quality. Then you need to have a team and assess their skills. Finally, you have to experiment. Evaluate candidates for yourself. Try to prototype small bits before settling on the game engine. Finally, small tip. If you are an indie, usually you do not need to care about that much, as smaller games can be run by a wide variety of game engines. Just check whether they really support your target platform. For instance, Unity is not guaranteeing WebGL builds to work on mobile platforms still. After this introduction, we can finally check what's inside game engines, what it covers, and then peek under a few hoods. Game engine architecture can be simply described as huge. From a certain perspective, game engines are like operating systems, and many consoles were not more than game loaders in the past. But that's actually hard to see when all you observe is the top of the pyramid, the actual game. So here we start on the top, with a game-specific layer each game has, and each game needs to adapt heavily. Game-specific subsystems are always developed for each game separately. You can see them as game business logic in a sense. You need to declare and implement all the items, weapons, vehicles, puzzles, AI, camera movement, eye candies specifically for each game. But that's not all. One real-world example. Warhorse Studios decided to use CryEngine back then, when they started working on KCD. But AI subsystem of CryEngine was implemented for first-person shooters, so all NPCs were meant to be rather short-lived. Now contrast it with open-world RPG, such as KCD, where you need villagers to have their lives. And so, the whole AI subsystem of CryEngine was replaced completely. Then we are getting to game-agnostic layer, or game-independent layer. A layer where all boxes are typically needed by all games, with few exceptions like online multiplayers for single-player games, or perhaps skeletal animation for simpler 2D games. But a lot of the rest will be used somehow, and depending how many elements you will need to have in your games, they might require some adaptation or optimizations if you find them underperforming. Then we are getting to game engine foundations, which is surprisingly wide. It can be split between core systems, which contains crucial functionalities required to build higher-up systems, and resources, various loaders and managers of game data, which need to be loaded and discarded during runtime. All games need all subsystems in here. You cannot have a game running without math or memory allocation, random number generators, serialization, file operations, and so on. Regarding resources, you might not need all of the listed types, but you will have some, so Resource Manager is something each game engine ought to have, as you require your game engine to be able to load and unload scenes or game world parts as game runs. Finally, there is a platform level, which contains low-level routines which are using platform-dependent routines, wrapping them into facades or adapters that are then used higher up the layers. And these are crucial in order to have truly multi-platform engine. Imagine you will have to handle multi-platformness on the game-specific layer, implementing one feature for every platform separately. Doable, but not something you would cherish. That's why I have labeled game engines as operating systems of their own kind, because they have to have strong platform independence layer, and their custom core systems, which are then shaping the rest of the code base. In order to work with them, you have to speak their language. That is, GameEngines either embraces but more often replaces various standard C and C++ libraries and abstracts them with their own model. Everything above those systems then speaks a custom game engine proprietary language, and that's why it is typically hard to replace a single box within this architecture. If you would like to bring another third-party middleware SDK to the game, you have to first wrap it into primitives the rest of the engine understands, and only after then you can use them. More complex interface your middleware has, more complex the integration will be. The worst what can happen is the clash of versions of various utility libraries like Boost or STL that are typically integrated deep within the middleware, and if middleware is not designed the way that they are replaceable by having their own independent layer, it might be even practically unfeasible due to the excessive effort you will have to invest into such an adaptation. That's why it is a big decision choosing a certain game engine as your weapon of choice. You wanted to use them just for simple 2D side-scroller and export it to multiple platforms, but you might encounter glitches along the way that might be hard to solve. Finally, to all this, there are two possible stacks how those layers can be wired or coupled within the game, and that concerns how the game world editor or builder is implemented. Either the editor is independent, that is, it sits alongside the runtime engine, thus having any tight couplings to it, or the world builder is built in and sits on top of the runtime engine. If the world builder actually sits on top of the runtime engine, then if you make some extension to it and you make a bug, it may prevent the engine from running or be compilable at all, which can mess with other people's work a lot. So be aware of what you're coding. If that would not be enough, game engines should be able to integrate with third-party solutions that are being used for specific tasks like 3D modeling and animations. That's because when producing a game, even as indie, you will be dealing with something that is called asset pipeline. That is, how are you going to be authoring content for your game? Game Engine and its editor are final integrators and consumers of results of other tools like 3D modeling and animation tools like 3D Max, Maya, Blender, or procedural assets creators like Houdini. Ideally, you would like your engine to be loading changes automatically, and the holy grail is to work in third-party editor and have your changes being propagated to your game during runtime of both tools. On the other note, but still in the same part of the asset pipeline, you might need sometimes to work with development data, which are of poorer quality. The problem is that loading times for scenes with quality models and animations are high, and if all you want to test are gameplay triggers, you do not need that fancy graphics and wait for their loading. So all this is a task for resource management. It defines how assets are loaded, processed, adapted, and thrown away during runtime, but not only. Resource management has three parts. First, you need exporters, something that can get the asset out of digital creation content tool, a shorthand. Second is a resource compiler that adapts the resource for the use inside your game engine. Finally, you need resource linker that can composite this data into packages. For instance, a character in the game consists of a model, skeleton, rig, textures, animations, and there are multiple tools you use to compose such a character. That means that assets may have dependencies between themselves, and those dependencies must be described. Once some part of the final asset or package changes, it may trigger their rebuild. These dependencies are required even during runtime to provide automatic load and unload of assets. During runtime, the resource manager ensures that each asset is loaded only once, provides that autoload and unload, therefore managing the required memory for assets and handles streaming if required. Finally, it must be noted that resource loading is typically a very demanding operation. As such, you cannot request it synchronously, as it would cause a spike tearing down the frame rate. As the result, you need to load everything at once at the beginning of the level or a scene, or do it in the background, silently streaming in assets from another world chunk which the player is just approaching. Now we could start talking in details about other things, detailing what it means to have high-quality implementations for them. But that would require more time than we have here, so let's exemplify only a few more, which you might skip as something that is simple. Like assertions. Why they are important? Why should I care? Well, during the development, your game-specific layer will be changing a lot. Without assertions, things will be breaking on a whim. You need to specify checks that will be removed during the final build for speedups. True, but during development, that can save you a headache. Or math. You might have thought that math is a solved thing. Well, you might get surprised to receive different results based on platform your game might be run on. Guys from the Factorio game has written their own math library exactly because of this. They found out that their simulation deviates on various platforms, which is weird as the codebase was the same. What they found out were subtle differences in more complex operations like square roots, trigonometry and such, which pile up and cause the simulation to deviate in the end. A bugger for multiplayer that should work between different platforms as well. There, you want to rely on the simulation being the same, as it allows you to replicate less stuff over the wire, allowing for shorter latencies. Or memory management. Isn't that supposed to be a work for an operating system? Well, yes and no. The thing is that new and delete operators are slow. Anything that relies on the OS services is slow in general, and you do not have a control over it, which is bad if you're trying to run a game that is a real-time simulation. Or the precise role of resource manager. How hard could be loading data into the memory and disposing it? How about you want to ship your game with assets of different quality given the platform you are targeting? Will you be recreating your scenes for every platform, or you would like Resource Manager to allow for the specification of data of different quality under the same resource ID? Or building. When building, are you going to manually go through all the resources, flagging them which are really useful, or you would like Resource Manager to compute that automatically for you and leave out the rest? And how about runtime modification? Would you like to be stopping the game every time you need to swap assets, or you would like Resource Manager to allow for runtime modifications of your game objects? Then, of course, renderer. Game needs to be visual nowadays. You won't get much attention with text-based games. Apart from 3D rendering and 2D rendering, there is one component you should pay attention to. That is a scene graph and its culling. When frame rate is dropping for your scene, good chances are you're rendering too many triangles. Of course, complexity of shaders may be troublesome as well, but usually your models are huge as well as your scenes. Well, for models, we have level of details. If a model is far away from the camera, we replace it with low poly model or a billboard really. But what if your scene is simply composed of too many objects? Then it is the best to know which game objects need to be rendered and which not. Open world has it hard, but for corridor games or dungeons, you might need to be hinting the renderer that there are some parts it does not need to be considering at all, because they cannot be seen, so-called scene graph culling. And for that reason, you might want an engine that allows you to customize this feature, as it heavily depends on the kind of scenes you will be creating. And we could talk about following components as well, but we would not get very far. Instead, I would refer you to the overview linked at the top, which is providing a bit more information about those components. But actually, each bullet here is craving almost for a separate set of lectures or a course really, like AR or physics or network. These are all intriguing and vast topics and fields whose results game engines are integrating. However, this is making them separate topic really. What is native to a game engine, which is its core business, is that they are soft real-time systems that need to integrate many things inside them while being multi-platform. And that makes the foundational layer of the game engine architecture quite important topic and native to game engines, so we will continue exploring that. Let's start with messaging system. That is, how should subsystems communicate with each other, not resorting to tight coupling of the codebase? Typically for a game, everything is somehow related to each other. Every part of the game needs to interact with others, so it is very tempting to wire calls between various submodules and create a big ball of spaghetti call mess. However, it does not need to be like this. Instead, you might want subsystems to be communicating via some form of messages or events. One can learn from various remote procedure calls mechanisms, but essentially the idea is not to call subsystems directly, but be sending requests or reacting to events broadcast by those systems. One way to implement this is via generic message bus, to which you can send requests like play sound now, or create new scene entity, or propagate events like player wants to shoot, or another frame was rendered. If you do this, what you will get is a message bus that can log what is happening in the system. By just observing the messages on the bus, you can reconstruct what has been happening in your game, which is a great tool for debugging complex scenarios. Moreover, you can start sending ad hoc messages via console during runtime to observe behavior of your subsystems under various conditions, which is another plus for the debugging. Then, a good engine is certainly an optimized one. Optimizations are the key to higher frame rates. There are some rule of thumb how to achieve that. Not really. Previously, like in 90s, it was easier. You had single-threaded game engine, CPU was expensive, memory was cheap. Now CPU is kinda cheap and memory is expensive, so it's harder to utilize CPU completely. And the reality is thus complex nowadays, and intuition will not help you much. All of the following rule of thumbs does not need to be true nowadays. In the nutshell, you always have to profile. One thing to bear in mind is the architecture of RISC processors which are having multi-level caches and are pipelined. This means that ideally one wants to keep the processor busy all the time, meaning that the pipeline stages should always have something to do. But your code may produce code dependencies. There can be branching or cache misses, which will produce stalls within the CPU. Execution of the next instruction might need to be postponed because of that, like waiting for completion of previous one. which for instance means that accessing an element in the array using pre-increment can be worse than using post-increment. Why? Because in the former we can start accessing the array only after we increment the variable, whereas in post-increment the incrementation can be done sort of in parallel with the array read. Let's have another example of where the raw power is hidden. If your code is well profiled, then the majority of the time spent is hidden within very trivial things. Like in this trivial routine of determining how many digits given number v has. The code looks pretty simple and understandable, but it is the most performant one. Apparently not. We can do more comparisons and additions and fewer divisions, which will perform better despite the number of ifs per iteration. Note that this is not something a compiler can really come up with. This is not a trivial loop unrolling, as we divide variable v only once per iteration. But we really just scratched the surface of things. There are tons of materials on low-level optimization like this out there. Then there we have memory management, and I'm not talking only about main memory here. What you actually must have in mind are transport times between different types of memories and CPUs, which have their own caches. That's where true power lies. Notice how awfully slow it is for CPU to be reading from the main memory. That is how many cycles your CPU will waste waiting for data to arrive. Well, this picture is old. Nowadays it's probably 100 cycles for fetching something from the RAM, but still it applies. CPUs can do a lot of things than just wait for data from the main RAM. And there are more numbers like that. Like on the left side, we have the processor, the black dots representing nanoseconds. Then we have main memory, referencing it starts at 100 nanoseconds. So a blue dot is 100 nanos. Then we have green dots dealing with SSD random reads. One green dot is 10 microseconds. Finally, we have red dots like disk seeks, reading megabyte from average SSD, or packet round trip around half of the world. So one red dot here is 1 millisecond. Notice how referencing L1 and L2 cache is much faster than fetching something from the main memory. Interestingly, things have not changed much since 2016, which is a bit extraordinary. We had 5 years in which main memory loading times have not changed, meaning that CPUs are much faster at crunching instructions than data loading for 5 years in a row now. Network got faster, though, but SSD did not. So having these numbers in mind, let's talk about memory management now. So, first 2 tips. Malloc and new are slowed. Avoid them. Continuous memory access is the key. Cache misses may cause your code to run more than 20 times slower. Align your data you're crunching as much as possible. So let's address the first tip. Game engines need to provide their own memory manager. They allocate the memory at the beginning and then governs that by themselves. And for that you may utilize different strategies. And as usual, different memory allocation strategies suit different games, and general approach may be worse than specialized one. So first, stack-based memory management. So we have our big chunk of memory allocated via malloc or new, which we did at the start of the game engine. We maintain one extra pointer that points into the memory. And then, when someone requests a new memory, we return this pointer and move it forward according to the size of the data requested. This has pros and cons. Advantage is that in corridor games, you just allocate what's needed for the level and unloading of the level is then pretty simple. You just move the pointer back to its origin before the level was loaded. This way, you never get memory fragmentation. That is small holes of memory inside your big array you're managing. Disadvantage is that you cannot really have on-the-fly dynamic allocations in the allocations, as you have no means of creating that holes in already allocated space. But you can live with that. In games, as the rule of thumb, You should not be generate garbage per frame, meaning allocating data every frame and discarding it should be avoided. Use the stack for that, not the heap. But if you really want to have dynamic allocations per frame, well, to be honest, they are sometimes needed, then you can have double-side stack-based memory management. Similar idea, but this time we are having two pointers. When allocating data, you give memory from the left, and so you have a left memory pointer. When the allocating memory for the frame, you're going from the right, so you have right pointer to the memory. And when the frame ends, just reset the right pointer back, thus quickly discarding the data. Sometimes even that is not enough, if you need to be able to pass dynamic data in between frames. So you cannot live with only single frame allocator we have just described, and need two. One way to implement that, if level data are fixed, is to first load level data and then use again both sides of your memory space. Two sides mean space for two frames, so you can be passing data between frames that way. Another very frequent practice is pooling. Actually creating complex objects can take a lot of time as you have structs and classes nested in each other. Is it therefore a waste throwing them out? Or you need to be instantiating a lot of small things like bullets, and you do not want to recreate them over and over again. In which case you might use pooling. You define a memory budget for your pool like 200 bullets on screen at maximum. Take size of data for each bullet and allocate memory for 200 bullets. Then you offer two methods, get and back from the pool. When you need a new bullet, you ask the pool via get to obtain a pointer onto a bullet that is not being used yet or currently. When you want to discard some bullet, you pass that pointer back to the pool. In theory, that sounds easy. In practice, you need to track which instances are being used and which not. This means you need to maintain two linked lists within the memory. One linked list of alive instances and one linked list of not used instances, so you can implement get and back with O1 time complexity. Importantly, this trick is usable with garbage collected languages as well, because even there you can be recycling instances. Instead of discarding those instances, you just return them to the pool. The implementation is rather simple there, as all you need to have is a queue of unused instances. If you do not have anything in the queue to be reused, you create a new instance. When returning instance to the pool, you add it into the queue. So if you're requesting a new instance and you have something in the queue, you just dequeue it and return it. This way, you can avoid garbage collector spikes, which is again something you want to always do in games. Finally, if you really want some part of the memory devoted for random dynamic allocations that are not fitting any previous use cases, you can resort to smart pointers. When returning a pointer to some data, you actually return a pointer to a pointer, wrapped in an instance that will spare user of double dereferencing that manually. This way you can even defragment your memory because of holes that can appear there because of the allocations. The only consideration here is that double dereferencing is a bit slower, and defragmentation smells of CPU spikes, so you need to be careful about that. Finally, creating your own allocators is only the beginning. Know that people want to use containers in their code, which means dynamic allocations. So when choosing your collections library, be sure it allows you to slip in custom allocators. Now for the latter problem, data structure alignment. Note that CPU can work only with aligned data, usually meaning 32-bit alignment. So if you are not careful enough, you might declare a struct that will be bigger than the data it is holding. Like the example here, see how 8 bits data are being padded? So do not waste the memory and think about the order of declarations. You might ask why compilers will not optimize this. That's because in C you can write to the memory directly, and you might rely on this struct layout. Finally, be aware that CPUs are always loading larger chunks of data from the memory read, because why not? The memory bus has some width, so why not to use it when you're at it? Now consider this struct and accessing A and B in single expression. This will most likely create 2 cache misses instead of 1. Another interesting topic where you can save a lot of performance as well as memory are strings. Strings are ubiquitous in game development. Everything is named somehow, be it image or audio file, a scene, an NPC entity, or in general, a trigger, text, etc. The things that texts are good for humans, but not for computers. They frankly don't care. For the purpose of computation, it does not matter in theory where you're labeling things with strings or ints, but down on performance level, that is a big difference. Comparing 2 strings is much more time consuming than comparing 2 ints. On the other hand, debugging your gameplay code that states that 128 fire and 567, which used 123 as defense and retaliated with 267 and killed 128, is kinda pain. So ideally, you want human readable string identifiers during development, but not in your game when you're shipping. Although there are different usages for the strings as well, not only as identifiers or debugging, but also as a game text that requires localization. But back to the string as unique ID. As usual, there are different approaches to the implementation of a string as unique ID. First, you can use macros. So in the code, you can write macro that will take care of translating that text, usually using some hashing functions. And note that there are even hashing functions that support concatenation, which is very handy. Second option is to use bidirectional maps for mapping between strings and IDs. This way, you can always translate your string back when needed, usually during development. Finally, you can always wrap a string into some small object and pass that object around, which has a big advantage during debugging. When inspecting variables on the stack during stepping, you will actually be handed with a string along the number, so you will know what you're looking at. As we are in C and C++, we can do some smart things like defining a custom type ID and some macro text, and then include their different implementation depending on the build type, so you can have advantage of strings being persisted during development and stripped during the final builds. Another chapter is localization. The thing is that you never want real text in your code. You will always have some kind of the database with text because of localization. This will usually work utilizing some kind of hash tables or maps or dictionaries. For some key, you will store an actual string to be used as chosen by the player and language selected. At the beginning of the lecture, we said that game engines and frameworks differ from middlewares, and by implementing a game loop design pattern. An endless while cycle that is broken only by a request to terminate the game and thus the game engine itself. Why is this distinction important? That's because you need to maintain some coherency of subsystem execution. You need to order their updates as they may depend on the results of each other's work. Now, how you could do that if a middleware is having its own closed update loop running in a separate thread you have no control over? You probably cannot. Therefore, middlewares are not having their own loops and offers just an entry point update method that you're out to call from your own game loop. As usual, there are a few approaches how this rather simple idea can be implemented, and as usual, in the end, it is not that simple at all. As you already know, a movement on the screen is the illusion of presenting many frames per second. Biologically speaking, we humans are sampling the reality with limited frames per second, so after a certain threshold, we start perceiving fast things as moving continuously. Do not be mistaken with old saying that 24 or 25 frames per second is enough. You can surely spot a difference between 25 FPS on 100 Hz monitor and 100 FPS. But in general, anything above 30 FPS is acceptable by many. Every game engine therefore has at least a render loop. that is trying to run either as fast as possible or with some kind of cap like 60 FPS. But rendering is not the only subsystem game engines have. You need to read input, you need to update physics, you need to update AI, you need to update simulation, and so on. And not all those subsystems need to work every frame. Like AI is sufficient to update 10 times per second for high fidelity results. Or some systems cannot stick with variable frame rate like physics, which needs to be fixed step in order to lower their sort of non-determinism. In the end, all subsystem loops will be somehow realized in the context of within one master game loop. So first, good old-fashioned single-threaded implementations. Here is an example of the single-threaded game loop inspired by the famous game Pong. After game initialization, or should we say game engine initialization, so after init we enter the loop. There we process the inputs, check for exit, and if the game should continue we move pedals, ball, check for collisions, and if there are any we resolve them. It might look funny comparing this loop to game engines like old Unreal Engine 1 or 2, but the pattern is there, even subsystems, we might say. And if we wrap all Pong's code into such subsystems, the loop will remain. And that's how single-threaded game engine worked back then. A list of subsystems that were updated every frame in certain order. Another example of the loop pattern can be found in Windows application. If you are to implement a window application in Windows, you need to enter so-called window message pump, that is relaying events between windows. In this top-level loop, you have to check every frame if there isn't a message to process, and if so, handle it. Else, just tick your game engine. The basic idea is to service Windows messages whenever they arrive and to service the game engine only when no Windows messages are pending. One of the side effects of implementing the game loop like this in Windows message is that Windows message take precedence over rendering and simulating the game. As a result, the game will temporarily freeze whenever you resize or drag the game's windows around on the desktop. Single-threaded loop can also be callback-driven. In single-threaded games, it is beneficial to be able to hook to certain steps of the loop iteration, so you perform some operations in sync with the rest of the code. One such example can be found in the rendering framework Ogre. At the lowest level, Ogre provides functions that can be called directly by a game engine programmer. However, Ogre also provides a framework that encapsulates knowledge of how to use the low-level Ogre library effectively. If the programmer chooses to use the Ogre framework, he or she derives a class from Ogre Frame Listener and overrides two virtual functions, frame start and frame end. As you might guess, these functions are called before and after the main 3D scene has been rendered by Ogre respectively. Or you can have it other way around, having a list of events to crunch. That is, you have a discrete simulation where you have events like frame begins, rendering, audio event, input read, etc. You can have then various subsystems registered to those events. The difference from the previous callback loop is that the main while cycle is crunching those events, which may be dynamically added to the queue, so you do not have fixed implementation of the loop iteration as in the previous example. Of course, these are more or less things of the past, deprecated by the advent of multi-core CPUs, which are widespread today, and so all modern game engines are multi-threaded now. Around the time of PlayStation 3, multi-threaded engines were being popularized and really shouted for as the next-gen thing to improve performance and increase FPS, though PS3 has taken it a bit to an extreme. Let's look at Sony PlayStation 3 architecture. The PS3 main CPU is called the Power Processing Unit, or PPU. It is a PowerPC processor, much like the ones found in the Xbox 360 on the right. In addition to this central processor, the PS3 has 6 coprocessors known as Synergistic Processing Units, SPUs. These coprocessors are based around the PowerPC instruction set, but they have been streamlined for maximum hardware simplicity and maximum performance. The GPU on the PS3, known as the RSX, has a dedicated 256 MB of video RAM. The PPU has access to 256 MB of system RAM. In addition, each SPU has a dedicated high-speed 256 kilobyte RAM area called its local storage. Local store memory performs about as efficiently as an L1 cache, making the SPUs blindingly fast. The three cores and the GPU share unified 512 MB pool of RAM, which can be used for executable code, application data, textures, video, RAM, you name it. The SPUs never read directly from the main RAM. Instead, a direct memory access DMA controller allows blocks of data to be copied back and forth between system RAM and the SPU's local stores. These data transfers happen in parallel, so both the PPU and the SPUs can be doing useful calculations while they wait for data to arrive. Xbox 360, on the other hand, has more regular PC-like architecture, having 3 cores with shared 1 MB L2 cache and 512 MB of GDD3 RAM shared also with GPU. However, programming for PS3 was a nightmare. The architecture was so different and new it gave programmers headaches. From endless nights because moving data back and forth between PPU and SPU was not an easy task. PS4 thus reverted to more standard architecture, which is more or less similar to Xbox One. The PS4 8-core Jaguar CPU is a high-performance computing device. Yes, it runs a slower clock rate than PS3 PPU and SPUs, but it makes up for this by including hardware that makes less than optimal code. In other words, pretty much all game code run much faster than it would be run on PS3. For example, the Jaguar supports advanced branch prediction circuitry, which can correctly recognize all sorts of common branching patterns in your code. This means a lot fewer pipeline stalls in branchy code. At the end of the day, what this means to game programmers is that they can focus their efforts more on making great games and less on trying to rearrange their source code to eliminate branches in an effort to buy back lost performance. Xbox One architecture is very similar. There are differences, but they are not that much noticeable. So, having this console described, there is no wonder GameEngine started to move towards the multi-threaded model. Though that was not an easy task, as one has to unwire interdependencies and watch out for race conditions. So the first attempt to utilize multicores was fork-join-loop model. It's a hybrid approach to say, you still have a single loop, but that gets forked occasionally in subsystems where it is easily achievable. Usually subsystems which are crunching a lot of small tasks, like pose blending, or of multiple characters, or simulation of game objects which updates independently, and so on. These were immediate candidates that could have been forked right away without refactoring the whole engine codebase. Next step was to push subsystems into their own threads, having them crunching whatever they need to sort of independently to other systems, pausing only when they require data from the others. This resulted in much more load on the CPU cores, but still were producing blind spots in the execution of threads and thus cores. For instance, Unity is still pretty much of the thread per subsystem architecture, though developers are trying to move towards more efficient job model. Unity still has its main thread, audio thread, physics thread, and rendering thread. The holy grail of multi-threaded loop model is job model. Originally advocated in PS3 actually, however the time was not right back then. Job model differs largely from the thread per subsystem model, that you only have main scheduler thread and the job threads and many job threads. You are constantly creating a directed graph of jobs, which defines dependencies to each other, having the scheduler thread figuring out their ordering and dispatching them for execution to job threads. Even more, if the main thread has nothing to do, it crunches jobs as well. In theory it works well, in practice it is difficult to achieve this. The right amount of separation between jobs and split them into smaller chunks, so big long-running jobs did not create blank spots, as other jobs that depends on them need to wait for their single-thread execution. This approach is used a lot by Unreal Engine 4. Here is the list of consideration when creating a job, and I will leave it up to you to your contemplation. There is, however, one consideration that can bug your performance, which is called the false sharing problem when you use job in a wrong way. In symmetric multiprocessor systems, each processor has a local cache, and the memory system must guarantee cache coherence. False sharing occurs when threads on different processors modify variables that reside on the same cache line that is shared between respective CPUs. This invalidates the cache line and forces an update, which hurts performance. This article, the linked article, covers methods to detect and correct false sharing. In a nutshell, if you have jobs which are reading and modifying similar data, a false sharing may occur, stalling the processor. So watch out what data are your jobs crunching in parallel. Connected to these low-level issues of CPUs and memory caches, a new type of game object organization has been emerging. This is not connected directly with the game loop, but more with how you structure your gameplay objects. A professor from Carnegie Mellon University once said that object-oriented programming is both anti-modular and anti-parallel by its very nature, and hence unsuitable for a modern computer science curriculum. I'm not convinced with anti-modular, but I agree with anti-parallel. The problem of OOP and composition of object is that the composition happens via pointers often, which means one game object is spread all over the memory, and so poor CPU might get into multiple cache misses when evaluating single line of OOP code that reads data from a few objects. The idea then is to see the gameplay code as system operating over some data, or actually multiple systems operating over some data. Hence the name data-oriented design as opposed to object-oriented design. In data-oriented design, you model your entities. You do not model your entities with objects, but rather with a number or a set of numbers which points to arrays of components the entity is formed with. The trick is that those arrays are created so they are easily digestible by so-called systems, which ought to be performing gameplay updates. Like for instance solving spreading of fire by having a flammable component and fire system that crunches propagation of the flame across the array of flammable components. The trick is that we will always be iterating over the consecutive array of elements which are going to be small, thus keeping CPU caches happy, yielding big performance improvements. Again, the theory is nice, but this is not suitable for all kind of gameplay codes, but it can serve you as an example how you can squeeze more performance out of the CPU with correctly organizing your gameplay objects and data. And that's it for today. Thanks for watching. And here are a few more links you might want to explore, or just Google keywords yourself. So until next time.